Welcome to AI Frontiers. Today's episode is titled Robotics from Digital Dreams to Real-World Impact, focusing on frontiers in cs.RO research for November 2025. We'll explore 42 groundbreaking robotics papers featured on the arXiv preprint server's cs.RO category. This episode unveils how robots learn, adapt, and collaborate, examining advances in simulation, perceptual intelligence, and building trust between humans and machines. We'll also spotlight a standout paper of the day for in-depth insights. Join us as we journey through the latest innovations shaping the future of intelligent robotics. Behind every smooth robotic movement lies a silent contest between digital algorithms and unpredictable physical reality. Picture a robot delicately picking up a glass in a real kitchen. While its actions may be informed by extensive simulations, the real world often throws unexpected challenges. This persistent sim-to-real gap is central to robotics research. How do machines achieve the adaptability and resilience of humans? This episode uncovers these hidden battles, revealing the ongoing efforts to bridge the divide between simulated training and real-world performance. The cs.RO category represents the intersection where software engineering meets the tangible demands of the physical world. Robotics research integrates artificial intelligence, mechanical and electrical engineering, and human factors to address complex challenges. In today's episode, 42 research papers have been distilled into key themes and notable discoveries. The purpose is to illuminate both the technological advances and the human narratives driving innovation, demonstrating how breakthroughs in the lab translate into real-world applications that impact daily life. Robotics can be envisioned as a grand orchestra, seamlessly blending artificial intelligence, engineering, and physics. In this analogy, each domain expert serves as a musician, contributing unique expertise to the ensemble. Physics acts as the conductor, ensuring every element remains synchronized and precise. The success of robotics is not evaluated solely by theoretical performance, but by reliability and adaptability in real-world environments. Robots perform in diverse settings: factories, hospitals, oceans, and homes, where their effectiveness is measured by tangible outcomes. A major theme in current robotics research is bridging the sim-to-real gap. Robots often learn complex skills in idealized virtual simulations, but real-world environments introduce unforeseen variables and complications. This challenge parallels pilots' training in flight simulators, which cannot fully replicate the turbulence and unpredictability of actual flight. Notably, Gia and colleagues propose decoupling motion planning from low-level control to enhance robustness in bipedal robots. The sim-to-real transfer process is essential for adapting virtual skills to physical hardware, underscoring the importance of practical validation beyond simulated settings. Robots are increasingly equipped with multimodal and semantic perception capabilities, enabling them to see, hear, and feel their environments for richer interaction. Advances include audiovisual integration, tactile sensing, and language-informed planning. For example, Slot VLA, introduced by Joe and collaborators, focuses on object-based scene understanding, allowing robots to identify not just objects, but also their properties and relationships. This approach moves beyond simple recognition. Robots are learning to interpret environments similarly to humans, understanding context and meaning for more effective decisions. Ensuring that robots are safe, transparent, and reliable partners is a central concern in human-robot collaboration research. Innovations such as the Unified Fall Safety Framework by Sun and colleagues draw inspiration from how toddlers learn to recover from stumbles, combining prevention, mitigation, and rapid recovery. Reachability analysis is employed to guarantee robots avoid hazardous zones. Comparative studies examine human and robot performance in complex tasks. highlighting the evolving trust and teamwork required for effective collaboration between humans and intelligent machines. Several key findings from this month's research can be viewed as impactful mini-stories. Time-aware policy learning, introduced by Gia and co-authors, enables robots to adapt their operational pace based on situational context, improving both efficiency and robustness. Lightning Grasp, developed by Wang and team, facilitates instant and diverse robotic grasping by decoupling geometric reasoning from search, greatly accelerating manipulation tasks. Huang and colleagues announced Raspi2 USBL, an open-source Raspberry Pi-powered acoustic positioning system that democratizes underwater navigation. SlotVLA advances structured, explainable object relation reasoning for multitask manipulation. Unified fall safety policies enable robots to recover from slips with agility, drawing inspiration from human development. The featured paper of the day is Myers et al.'s Testing and Evaluation of Underwater Vehicle Using Hardware-in-the-Loop Simulation with HoloOcean. The core challenge addressed is the high cost and inherent risk of conducting field trials for autonomous underwater vehicles. Myers and colleagues propose a solution that connects a high-fidelity virtual ocean environment, powered by HoloOcean 2.0, directly to physical robot hardware. The simulator and real robot interact in real time, providing a safe, scalable platform for rigorous testing. Integration with ROS2 broadens accessibility for the global robotics research community. Hardware-in-the-loop, or HIL simulation, is central to this research. In this setup, the physical robot operates as if it were truly submerged in the ocean, receiving real-time feedback from the virtual environment. The simulator processes the robot's actions and simulates underwater sensor responses, creating a highly realistic testbed. Parallel experiments demonstrate that outcomes in the virtual environment closely mirror those observed in actual field trials. This approach enables researchers to validate and refine control and navigation algorithms safely and efficiently, illustrating how HIL bridges simulation and reality to accelerate robotics innovation. The motivation behind Myers and colleagues' work is to expedite underwater robotics research, reduce experimental risk, and democratize access to advanced testing environments. HoloOcean 2.0, combined with the Coog UV platform, enables researchers worldwide to participate in accessible, cost-effective experimentation. Compatibility with ROS2 ensures seamless integration into existing workflows, fostering widespread adoption. The virtual playground, created by this system, encourages iterative experimentation and refinement, ultimately allowing more teams to safely test, validate, and innovate within the field of marine robotics. Looking ahead, the future of robotics is akin to cultivating a thriving garden. Advances in high-fidelity simulation and open-source tool development continue to lower barriers to entry, enabling broader participation. Physics-informed learning paradigms are being pursued so robots can internalize the underlying rules of the real world, not merely statistical patterns. The convergence of vision, language, and action models promises deeper contextual understanding. Emphasis on safety and trust will enhance partnerships between humans and robots. Each experiment and research contribution acts as a seed, gradually enriching the capabilities and resilience of the field. To conclude, robotics is rapidly evolving by integrating advances in perception, learning, control, and safety. The sim-to-real gap is narrowing, although significant challenges remain. Open-source tools and advances in interpretability are democratizing robotics innovation. Listeners are encouraged to explore the referenced papers for more comprehensive insights. Engaging with ongoing research and discussions will contribute to shaping the next generation of intelligent machines. This presentation was synthesized using GPT 4.1 for summarization and narrative construction. TTS synthesis technologies and image generation tools assisted in content creation, while human experts reviewed all material to ensure clarity and technical accuracy. While every effort has been made to ensure reliability, some oversights may exist. Full references are provided for validation. AI Frontiers aims to blend the strengths of cutting-edge artificial intelligence tools with expert human insight. Subscribe for deep dives into artificial intelligence and robotics research. Stay updated on the latest papers and emerging trends. Connect with a community passionate about intelligent systems and the future of technology. This is AI Frontiers. Thank you for exploring the future with us. In this podcast, we bring you the latest breakthroughs in computer science and AI, straight from the arXiv preprint server. From neural networks to quantum computing, we simplify complex research so you can stay ahead. Whether you're a developer, researcher, or tech enthusiast, AI Frontiers keeps you informed daily. Thanks for listening. If you enjoyed this episode, subscribe for daily updates. See you tomorrow with more cutting-edge AI insights. Disclaimer: this video uses arXiv.org content under its API terms of use. AI Frontiers is not affiliated with or endorsed by arXiv.org.